So we're in Unit 5 talking about astronomy, space, and gravity, and we're talking about gravity specifically right now. Newton extrapolated or stretched this amazing idea to the entire universe. And one of the most powerful and revolutionary ideas in the history of science. We have Newton's law of universal gravitation. Newton's law of universal gravitation says every object in the universe attracts every other object with a gravitational force. There's a formula, we're going to come back to it later. So this law means that the sun attracts Earth, Mars, it attracts me, it attracts the moon, it attracts you, it attracts everything. This law says that you attract the Earth, the moon, the book in front of you, pencil on your desk, everything. Newton developed the formula for calculating the amount of this force called gravity. He knew that this gravitational force depended on the distance between the objects. Remember, he had the force of gravity was a constant times 1 over the square of the radius, where r equals the distance between the two objects. He also sensed that this force depended on the mass of the two quantities. It depended on the mass of the attractor and the mass of the attractee. Using the Earth and the moon as an example, f of g equals a constant times the mass of the Earth, and f of g equals a constant times the mass of the moon. Newton also said that this attractive force did not depend on anything else. So putting it all together, the force of gravity equals, so here's K, it's a constant, the mass of the Earth, let's just say ME, times the mass of the moon, divided by the square of the distance. So then there's K. Our favorite value for K is 1, and when we developed the F equals ma formula, we made K equals 1 by choosing a new unit for force called the Newton. We can't do that again since the units already exist. We have mass, which is kilograms. We already have distance, which is meters, and we already have force in newtons. So we're going to have to do an experiment to find the value of K. So the purpose of this experiment, to find the value of the gravitational constant G, capital G. So the procedure, hang two masses, each 1 kilogram, at a distance of 1 meter apart. So here's a sketch. Here we have a 1 kilogram object. Here's our second 1 kilogram object. And center to center, they're 1 meter apart. Measure the amount of attractive force that they exert on each other. Use Newton's law of universal gravitation to calculate G. If the force of the attraction is 1 Newton, then G would be 1. The result of the experiment, the attractive force is 6.67 times 10 to the negative 11th newtons. So the value of G, including units, 6.67 times 10 to the negative 11th, and the units are newtons times meter squared per kilogram squared. So let's go back and fill in the formula above. So the force of gravity equals, first up was K, it was a constant, but we determined what it is, capital G, the gravitational constant. Then it depends on the masses. So we have the mass of object 1 times the mass of object 2 divided by the square of the distance between them. So Fg equals the force of the gravity. M, of course, means mass. R is distance. And G equals 6.67 times 10 to the negative 11th newtons times meter squared divided by kilogram squared. So on the next page, example 1, find the amount of attraction between two masses of 3 times 10 to the 10th kilograms and 2.5 times 10 to the 8th kilograms, separated by a distance of 50 meters. So let's start by writing our formula here. Force of gravity equals the gravitational constant times the mass of object 1 times the mass of object 2 divided by the square of the distance between them. Fg, so your gravitational constant, 6.67 times 10 to the negative 11th newtons times meter squared times kilogram squared. Mass of object 1, 3 times 10 to the 10th kilograms times mass of object 2, 2.5 times 10 to the 8th kilograms, divided by the square of the radius. So the radius is 50 meters, the distance between them, squaring that quantity. And a little bit about units. So we have kilograms here, we have kilograms here, so there's kilograms squared. We'll cancel here. We have meters squared, and on the bottom we have meters, and it's in parentheses being squared. So we can get rid of this m, and it will cancel with meters squared. Now I want you to be careful, because this squared doesn't go away. It still applies to the 50. So make sure that this stays here. And so that leaves us with units of newtons, which of course is the appropriate unit for force. Putting it into a calculator, 2.00 times 10 to the 5th newtons. Number 2, calculate the force of the sun's gravity exerted on the Earth to keep it in orbit. So let's go ahead and write our formula here. So let's go ahead and put some numbers into this formula. Force equals, say here's G here is, so let's see, the mass of the Earth, 6 times 10 to the 24th kilograms. The mass of the sun, which we can find on our sheet, so on the front side, about 2/3 of the way down, you see mass. All the way to the right is the sun. And mass is in terms of how many masses of the Earth. And so it says for the sun, 332,946. That is 332,946 masses of the Earth, Earth masses. So the way that we'll put that into this formula here like this. And just for the sake of our notes, let's label what's going on here. This is mass of the Earth, and these two terms together are the mass of the sun. So the next piece of this puzzle is the distance between the Earth and the sun. And so if you look at the same blue sheet at the very top, average distance from sun, 149.6, and that is in millions of kilometers. So let's write this in, 149.6, and that is millions of kilometers. But don't go anywhere yet. We have to be careful. This formula requires the use of meters, and so we have to change it. And so we know that 1 kilometer is 1,000 meters. And these two terms together will be squared. So when we use the data off the blue sheet, we have to be careful to make all the appropriate conversions. We can also cancel some things out. So for instance, here's kilograms squared on the bottom, here's kilograms. We can cancel those things out. And on the bottom here, this is meters squared. So we can get rid of this meters and this meter squared. and that'll leave us with newtons. And so we find that this force is 3.57 times 10 to the 22nd newtons. This is the force of the sun's gravity keeping the Earth in orbit. Example 3, calculate the gravitational attraction between Sam, 80 kilograms, and Susie, 50 kilograms, if they are separated by a distance of 0.5 meters. So we'll start F equals, here's the gravitational constant. Here is the mass 1, which is Sam's mass, 80 kilograms. Here is Susie's mass, 50 kilograms. And they are separated by a distance of 0.5 meters. And remember, we have to square the distance. And so once you put this in the calculator, you should get a number of 1.07 times 10 to the negative 6th newtons. This is the gravitational force between Sam and Susie, separated by a distance of 1/2 meter. Using Newton's law of universal gravitation as a guide, tell what the effect would be on the force of attraction between two masses if changes are made. So let's start off. This is going to be our basis. Mass M1 and M2 are separated by a distance of r. So mass 1 and mass 2 separated by a distance of r. So if we double mass 1, so let's say 2 times mass 1, and here's mass 2, here's the distance squared. What is the effect on F? Here's what's happened. 2, 1, 1 squared. We have doubled F. If you double both mass 1 and mass 2, so here's what we've done. Here's 2 over 1 squared. F multiplied by 4. If you triple mass 1 and double mass 2, here's what we've done. Force is multiplied by 6. If you double the radius, here's what we've done. 1 times 1. The force is 1/4 as great. Well, let's say you double the radius and you triple mass 1. Here's what we have. We have 3 times 1 over 2 squared. force is 3/4 as great. If you have R double M1 and triple M2, let's put all these in here. Here's what we get. 2 times 3 times 1/2 divided by 1/2 quantity squared. So what you have is 2 times 3, which is 6, and you have 1/4 on the bottom. So 6 times 4, the force is multiplied by 24. Looking at number 4, if the Earth's radius shrank by 10%, what would be the effect on your weight? So here's what we're looking at. So if this is the Earth and here is the Earth's radius, if the radius shrank by 10%, so we're looking at about here. And this is the new radius. What is the effect on your weight? So let's look at the gravity equation here. And for the masses, let's say that big M is mass of the Earth and small m is the mass of me. So G times big M times little m over the square of the radius. And so this one, we don't have to put in every single number. We can just use what we were doing in the previous chart. So we know that G is a constant, so the mass of the Earth didn't change, its radius just shrank. My mass didn't change, so those are both multiplied by 1. Here's what happened. We shrank the radius by 10%, so the new radius is only 0.9 of the original radius. And we're going to square that. And so what you find is 1.23 and you will weigh 1.23 times as much. Or put differently, your weight will increase by 23%. Number 5, find the weight of a 70 kilogram person standing on the Earth. Method 1, this is your unit 3. So weight equals mass times the acceleration of gravity. So the weight of a 70 kilogram person and the acceleration of gravity, we're going to use 9.8. The weight of this person is 686 newtons. Method 2 is from this unit. Using Newton's law of universal gravitation. Mass of the Earth. Usually we say 6 times 10 to the 24th kilograms. This time we're going to use a slightly more accurate number, 5.98 times 10 to the 24th kilograms. And here's the mass of our person, 70 kilograms. And this is divided by the radius of the Earth squared. So a lot of times for the radius we use 4,000 miles. Again, we're going to keep this kind of more accurate, 3,960 miles. And we need to change to meters. So 1 mile, 1,609 meters. All of that needs to be squared. So once all of this is calculated, Fg is 688 newtons. Pretty close, really. 686 using Newton's second law, 688 using Newton's law of universal gravitation.